Hello everybody, we will continue with our series on control design, and previously we have seen some linear control design techniques and then applications of that for aerospace autopilot design and things like that. So, towards end of this course we will also want to see some of the nonlinear control design techniques, and from beginning of this class to rest of the course we will study mainly on some of the nonlinear control design aspects actually. So, this particular lecture I will take you through what is called gain scheduling and followed by dynamic inversion, and then we will continue further from there. So, let us see this nonlinear control design techniques are sometimes most of the time nonlinear control design becomes a necessity, and even if you do linear control design then you make it operate like a nonlinear control design by invoking the philosophy of gain scheduling, and otherwise you directly go for some nonlinear control design technique either based on Lyapunov theory or based on feedback linearization or dynamic inversion, things like that. So, we will see some of those concepts as we go along actually. So, let us see first gain scheduling, and the topics that we need to discuss today is something like that. Primarily we will be looking at this philosophy of gain scheduling and some of the steps and issues, followed by dynamic inversion design, and that is also philosophy steps like issues and all that. And then probably one of the classes later we will also see that some of the like a high performance aircraft, that is like a fighter aircraft control design using dynamic inversion. Okay, so, that will also see not necessarily this class, but somewhat later on actually, and then we will also see advantages and issues of this DI design actually. So, let us talk study first this gain scheduling, and it is not a design approach per se, but it is a philosophy actually, and that is for making any linear control design work for any nonlinear systems, that is probably a necessity. Okay. So, we see this philosophy, and that is a very much accepted practice in industry as well, including aerospace industry. So, what is the idea there? Idea is kind of simple. So, what you have here is let us say you define some sort of a operating point. Let us say for example, there are some flight variable, let us say something like dynamic pressure as well as Mach number. So, your aircraft or flying object has to follow certain, let us say some domain of operation basically. Okay. So, in this domain it should fly. So, what you do here is like various operating point you take. Okay, you take various operating point throughout the region depending on your design approach and all that, and because this like about each of the operating point you linearize, and linearization is locally valid, we know that. So, in the local neighborhood you design different gains. Okay. So, in other words, let us say for this one this will be K1, this is for K2 and things like that. Okay. So, everywhere you design local linear controls based on local linear plants actually. Okay. And then you stitch them up using some sort of a interpolation routine. Okay. Now, if you have this kind of a interpolation, that means you are invoking this Mach number and dynamic pressure as free variables, that means it becomes like a 2-dimensional interpolation actually. So, anywhere to anywhere you invoke, suppose you are operating somewhere here, it should see this neighboring gains, and based on the neighboring gains you should try to interpolate actually what the gain should be at that point of time. That way you will be able to cover the entire domain actually. Okay. So, that is the philosophy of gain scheduling, and that is what is written here. So, first what you do is design local plants and then design local linear controllers, okay, based on those linearization of nonlinear system at several expected operating points, okay, based on the operating values of the scheduling variable. And remember, the scheduling variable or the interpolating variable need not be need not be state vector at all actually, because state vector is high dimensional and we do not want to interpolate the gain based on a very high dimensional interpolation. So, what you do? You normally select some sort of meaningful output variable, and in this case Mach number and dynamic pressure are very much meaningful aerodynamic parameters. So, based on that we try to interpolate, and we want to take this interpolating in other words meaningful output variables as much low dimensional as possible actually. So, if possible just one variable or maybe two variable, maximum three variable like that, which is tightly coupled with the system dynamics, number one. and number 2 which has to be meaningful. I mean, you cannot talk about something which is independent of the physics actually. Okay. And one important condition that you need to see is the scheduling variable has to be slow varying actually. It should not be very fast varying, because you do not want to excite this interpolation based on rapid change of variables and all that actually. So, it should be physically meaningful, as well as the quantities should preferably be slow varying, and we all know that Mach number and dynamic pressure are kind of slow varying quantities actually. Even for a fighter aircraft, these are the vehicle can maneuver, that is a different issue, but as long as the Mach number and dynamic pressure, these are functions of altitude and vehicle velocity per se. Okay. So, those things are kind of slow varying quantities actually. So, that is how it is taken there. So, coming back, this is what we need to do: design local linear controllers based on linearization of the nonlinear system at several expected operating points. Okay. And then obtain a nonlinear controller. Remember, this what we are really looking at is actually a nonlinear controller. Okay. Design because ultimately when you interpolate, the gain becomes nonlinear. I mean, the controller becomes nonlinear actually. Okay. So, we obtain a nonlinear controller for the nonlinear system by interpolation. Okay. That interpolating algorithm is nothing but the scheduling algorithm actually. Okay. All right. So, at any point of any operating point, we should have actual value of those scheduling variable, and the grid point data is already available with us. So, based on the grid point data, we try to interpolate and kind of get the control gain actually. So, that is the philosophy of gain scheduling. Okay. So, this is something what I have already told. What is the usual practice in industry? The scheduling variable may or may not be one or more state variables. So, we do not really go for a kind of state variable interpolation actually. So, the usual practice is to choose slowly varying meaningful output variables as the scheduling variable, and as I told, in flight control applications, dynamic pressure and Mach number are typically the accepted thing, because they are very tightly related to the physics, and they are also slowly varying actually. Okay. Now, the problem is the gain values that you are selecting. Okay, the individual gain values that you are selecting. Okay, those are okay. I mean, they can be selected based on like robust control phenomenon or whatever you want to do actually, but there the robustness is with respect to the linear plant or rather linearized plant. So, the moment you interpolate this gains, okay, the interpolated gain need not have all those robustness beauties actually. So, what you do even the performance condition may not be met simply because of interpolation. So, because of this difficulty, what is typically done is the robustness, performance, stability, etc., are usually justified from extensive simulation studies. Okay. So, this is what is practiced in industry actually. But anyway, having said that, after you do all this, what it really results is a semi global controller, because nobody restricts us from enlarging the domain. As and I mean, if you can build up your database in a big way, so you can keep on expanding your domain actually. Okay. So, that way it is what is like semi global control. It is not really a global controller per se, it may not be everywhere, but you can keep on expanding your domain if you have good amount of memory and good amount of computationally efficient interpolation scheme actually, because interpolation need not be computationally efficient either. The moment you have large amount of data table, to locate where you are in the data table itself takes a lot of time actually. So, even though philosophically it is possible to expand this domain infinite sense, you may not be able to do that in practice actually. So, essentially what it results in is a semi global controller depending on the selection of operating points and validity of linear gains also. Okay. So, the problem here is we cannot be able to predict a priori the subdomain in which the individual gains will operate actually. Okay, because sometimes the domain can be small, sometimes can be large. The individual balls around those operating points, the size of the balls are kind of not known to us a priori. That is the difficulty actually. Okay. So, anyway, that is how it is done in industry anyway. Okay. So, steps of gain scheduling I have already told you. So, we have to linearize the system dynamics about some operating point and then design the control gain based on that linearized plant actually. You can use pole placement, you can use LQR, you can use agent structure assignment, you can use you can use robust control theory, anything actually, whatever you want to do. So, based on this linearized plant you design a control gain actually. Okay. And then you have to repeat this procedure about several operating point as I described in the diagram actually. and you have to obviously store those gains in memory. Okay. So, online what you have to do is you interpolate the gains, stored gains whatever you have in the memory, and then essentially you get a nonlinear controller. Okay. That is what it is done actually. So, what are the issues? I mean, the advantage is very clear. I mean, we do not need a whole lot of nonlinear control design technique theory. We just rely on our knowledge on linear system design, linear control design theory, and then validity of this performance, robustness and all we do it from simulation studies. I mean, that is the advantage actually. So, there would, I mean, this too much of theoretical knowledge is not required, and too much of problems that are associated with nonlinear control design are also not required. Nonlinear control itself gives us lot of advantage, but it also throws some sort of difficulties as well. So, those are also not of primary concern to the designer actually, because designer does not have to do all those actually that way. And what are the issues? There are several issues actually in this design. That is why we need to study nonlinear control design as a nonlinear control system design. So, what is this? What are the issues in this rather simplistic approach? First thing is the linearized system good enough? I mean, that means what I told you before about each individual point. What is the size of the ball? We do not know actually. Sometimes it can be big, sometimes small. Whether we really we are really covering the entire domain or not, we do not know actually. So, there may be some sort of holes on the way, that means singularities on the way where the gains are not sufficient, it may not stabilize the plant, things like that actually. So, that is a big concern. What is the second one? Obviously, how many operating points to consider? Nobody tells us. Okay. So, in given this particular plant, you may select less number of points. You give another plant, you may select higher number of points, things like that actually. Okay. So, how many operating points to consider? I mean, that becomes certainly an open kind of open proposition actually. Okay. So, does the interpolated gain lead to stability? Need not be. Okay. So, and there are clear examples of loss of stability because of scheduling, where the individual gains were good, but once you schedule it, it loses stability actually. So, there are clear examples for that actually. Okay. So, that is a major concern for because of which we need to do several runs of simulation, different randomized simulation, what is popularly called as Monte Carlo simulation actually. We need to do a lot of simulation like that to have confidence on the design basically, and that is I think that may or may not be necessary in the nonlinear control design technique actually. Next issue, how easy it is to select a scheduling variable. So, that means okay, in flight control application, especially in stable aircraft design and all, people have done so much of study and then come up with Mach number and dynamic pressure as the scheduling variable, but that is related to physics and all. In general, it may be very difficult to do for other systems actually. Somebody has to do a lot of study to find good scheduling variables that will work actually. Okay. Because you are not interpolating the gains based on the state variable, you are interpolating based on some meaningful output variable which is of much lesser dimension actually. So, that may not be able to capture the physics of the plant actually, that is the problem. Okay. So, then next big issue is what if the parameters of the model are updated, and this typically happens when you go for a design change actually. Like if you go for a different design of the system altogether, for example, like wing configuration you want to modify a little bit, like bigger size, smaller size, or the dihedral angle and things like that, whatever you talk about, then the system is different. So, with respect different, you will have different parameters. Now, if you have a linear system design, then everywhere the AB matrices are changed because the original nonlinear system is different. So, now you have to go back to that I mean almost like ground zero, and then you talk about designing the gains again and then interpolating the gains again and things like that. So, that is a very cumbersome process in general actually. So, we do not need to do that if possible. I mean we want to we prefer to avoid that actually. So, this parameter update in the model or some plant dynamics getting changed becomes a big issue as far as design cycle is concerned actually. It takes a lot of time to retune it again. Then as I told, higher dimensional scheduling vector leads to complexity in interpolation. So, do not think that okay, if that is such a big deal of interpolation, let us go for like state variable interpolation, but that is also not a very good idea at all actually. Okay. As your multidimensional interpolation grows exponentially as the dimensionality increases actually. So, one dimensional interpolation you just need 2 neighbors to interpolate, 2 dimensional interpolation you need 4 variables to interpolate, 3 dimensional interpolation you need 8 variables to interpolate. like that actually. The neighboring node points will be the 2 to the power n sort of thing. So, we do not need to keep on expanding the number of free variables that way. Okay. So, if you really like, for example, if you have like 6-top equation where 12 states are there and things like that, then if you are very ambitious, let us do it 12-dimensional interpolation directly. Then the number of neighboring grid points that you will see for interpolation is 2 to the power 12 actually. That is a very big number to work with in realistic systems actually. So, that is a big issue there actually. Okay. And there is a very serious issue what is called loss of non-minimum phase property. Okay. And loss of minimum phase property, that means it leads to this non-minimum phase systems, for which the so called the other dynamics will go unstable, or this is if the system is of non-minimum phase, okay, then the zero dynamics or the internal dynamics will go unstable and all that actually. Okay. That concept we will see in the dynamic inversion anyway. So, if you are designing a tracking controller, for example, pilot command implementation is nothing but tracking controller. Pilot gives a command and your control system has to track that, whatever it wants to implement. So, in those situations maybe tracking itself will be okay, or suppose you want to climb height climb is probably okay, but the lateral dynamics may go unstable actually. So, those kind of situations are not very nice, and even if tracking is good, the minimum phase property and non-minimum phase property, things like that, will have reverse response in the beginning, and this reverse response in the beginning is very bad for the pilot actually, because it will lose handling quality properties actually. So, pilot will feel that the system is as if it is not behaving the way it wants to behave actually. Anyway, so those are many issues, there are many issues because of which this gain scheduling is not a universal design. We certainly need better approaches than this to kind of give some better design tools for the engineers actually. Okay. So, more on this gain scheduling probably you can read from this. This is actually a IEEE control system magazine article. So, it is not very difficult to read either, but it is very well written for anybody to kind of follow it, and then there are examples to demonstrate why gain scheduling is effective in some cases, not effective in other cases like that actually. So, my suggestion is to kind of read this and then have some comfort feeling. Alright. So, because of all these issues and all, what we really wanted is some sort of a substitute design, and that is what we proceed further and tell, okay, can we propose one such design approach, and then alternatives can be discussed later actually. Okay. And this is where we talk about dynamic inversion, where it is actually a promising substitute for gain scheduling. If you want to implement this, gain schedule need not be necessary actually, but gain scheduling is still an option within it. So, you may not be able, you may not need to invoke it for a large class of systems, but if you really want to do that option is still available within this. Okay. So, that is how it operates actually. Alright. So, let us proceed with this a little bit motivation and things like that, what does it do basically. So, let us talk about some sort of a curve like this. You can visualize from a number of applications, for example, like some UAV flying at different locations and then going somewhere and things like that. For example, this can be like waypoint 1, 2, waypoint 3, things like that. It has to fly and then proceed further. Let us simplify our ideas a little bit and tell, okay, let us consider this as some sort of a 2D trajectory. Okay. So, if I ask the question that whether this trajectory looks linear or non-linear, I am very sure in the first thought many of you will think that it is a non-linear trajectory, and which is not very non-intuitive either actually. It is very intuitive because without even knowing any other additional information, the mind tells us that this is the coordinate system actually. If this is the coordinate system, certainly this curve looks like a non-linear curve actually. But without changing the problem, that means without altering the trajectory itself, let us visualize the problem in a very different way. Then how about designing a coordinate frame that way? Okay. That means, I will not take this x y as coordinate system, but I will interpret this problem from the coordinate system x at y at actually. Okay. So, if I design this coordinate frame, if I am able to interpret this problem from this x at y at coordinate frame, then the distance remains constant actually. Okay. Distance from x hat to y hat at any point of time or any point of x hat remains constant actually. So, instead of this frame, if I look at in this frame, certainly this looks a much more benign problem actually. Okay. So, now within this modified coordinate frame I can design a control system as if it is tracking a step input actually. This is nothing but a step input. So, I can design a control system from this in this coordinate frame x at y at, so that the reference signal is like a step input, I need to just track it there. Now, once I do that job in that coordinate frame, I have to kind of go back to the original coordinate frame and then interpret the results in my original coordinate frame. Okay. So, obviously, the question here is, can we come up with some procedure, okay, for designing a coordinate frame first depending on the reference trajectory basically. Okay, depending on the problem whatever is given to us, can we design a coordinate frame which should be invertible actually by the way. For example, if I solve this problem in this coordinate frame, I should be able to come back to this and vice versa actually. So, okay, so if the transformation is invertible, certainly I will be able to do a better job actually. Okay, a much more simplified job actually. Instead of otherwise what you have to do, I mean I just have to originally if I look at it that way, then I have to design let us say many linear localized, I mean many local linear controllers and then have to interpolate and things like that actually. Now, I do not have to do that in this coordinate frame because everywhere the command is step input anyway. So, I just design it one go basically. Alright, so that is the whole idea there. But without going through too much of mathematics and all, I mean that is what you will find out in what is called feedback linearization chapters and all in nonlinear control books. I will try to simplify the kind of this approach and then try my best to give you a direct approach for control synthesis actually. Alright, so we will not digress this too much into whether when it is possible to transform, what is the transformation, and then it will, if you really want to do it, then it will demand these concepts of Lie algebra, Lie derivative, Lie bracket, then the concept of diffeomorphism, involutability, lot of concepts from differential geometry actually, before we really go to the topic actually. So, without doing that much detail, so we will not go that much detail, we will have some sort of engineering perspective to directly formulate a problem and then solve it without compromising the philosophy actually. Philosophy remains something similar, but you will not be able to answer your question directly that okay, what is the coordinate transformation you are looking at and what is the error, I mean what is the reverse transformation, inverse transformation and all that actually. Okay, those of you want to know, obviously nonlinear control books are available and probably Slotine only is kind of a good book to study this one chapter it is given there actually. Okay. Anyway, coming back to the problem remains like this. We want to talk about some sort of a design approach for nonlinear systems directly, and philosophy of dynamic inversion is something like this. We first carry out a coordinate transformation such that the problem appears to be linear in the transform coordinate. It is really not a linear problem. We are not linearizing the problem at all, but in the coordinate transform, in the transform coordinate system, the problem appears to be linear. Okay. And then design the control for the linear looking system, it is not really linearized system, but it is a linear looking system using linear control design techniques. Okay. Then obtain the the final controller, obtain the controller for the original system using an inverse transformation. That is what the entire philosophy of dynamic inversion relies on. So, intuitively the control design is carried out by enforcing some sort of a stable linear error dynamics. Okay. So, that is what we do and that is the key point that we will latch on to actually now. Okay. So, we want to design a controller by enforcing a stable linear error dynamics. So, whatever is the error, that error fellow should continue to see some sort of a linear stable linear dynamics, that is all we need to do. So, control design has to be done in such a way that whatever error between your actual output to the desired output should keep on seeing some sort of a stable linear dynamics actually. That is what we will latch on to actually. Alright. So, let us see this problem formulation and mathematical details a little bit. What we are doing here is, let us say we have a system dynamics of this form x dot equal to f of x u, okay, y equal to h of x, and y is the desired output. Remember, this need not be sensor output. Sensor output is something different and control design output is something different. Control design output is the kind of a objective output or the design goal what you want to take it actually. Okay. For example, if you want to land an aircraft, then height becomes some sort of a performance output. but you may or may not measure the height directly. You may be able to measure the range and the bearing angle sort of thing, and that height information is indirectly there in that actually that way. Okay, so you may not measure directly the height as such. So this one may or may not be sensor output actually. Okay, so that is what we need to clearly remember in control and filter design actually. There are a bunch of output which are performance outputs for which control design is primarily responsible, and there are bunch of outputs which normally the sensors keep on sensing. Okay, so these two may or may not be same, there may be some overlapping, they may not be overlapping, things like that actually. Okay. Anyway, certainly it is a good idea to directly measure it, I mean because if you have a direct information, nothing like that actually. Anyway, so coming back to this is the system dynamics that we are worried about, and this is the performance output that we are worried about. In other words, this output has to track some desired output actually, and that is the goal. Goal of tracking is like this: y should track or y should go to y star of t as t goes to infinity, and then y star of t is supposed to be the desired output or commanded output, things like that. Okay, and assumption here is y star is smooth. But that means if I plot y star t versus t, then I should not see any corner points and things like that. At least it should be smooth to the first order derivative sense actually. The first order derivative should be kind of continuous actually. Okay. Okay. Now, if the problem is clear, then we will I mean looking at this problem, it looks a little bit too much in the sense that this is a nonlinear system directly as it is. We do not know how this control I mean variable operates with that and things like that. So, to make our life a little bit simplistic, we will now further confine our discussions to a special class of problem where the problem needs to be affine and square actually. Okay. Affine means instead of control appearing that way directly as a nonlinear function, let the control variable act act on the plant in a linear manner. So, in other words, the plant is nonlinear, but it is nonlinear only in state, only in x variable, it is linear in the control variable actually. Now, the second one is this p equal to m, that means if you see these dimensional things and all, and in general x is a n dimensional vector, u is a m dimensional vector, y is a p dimensional vector. And then what you are assuming here is m equal to p, that means number of controls are equal to number of performance output. Okay. So, in the input output sense, the problem is really square actually. Okay. And then in addition we are assuming g y of x is non-singular for all time, and g y of x is not g x, g of x, g y of x is something we will define in the next slide, but it is certainly not g of x actually. Okay. But this particular matrix should remain non-singular for all time, and this is certainly a time varying matrix because it is a function of x actually. Okay. So, we will see that in the next slide what is this g y of x. Anyway, that is the problem. Problem objective is y should go to y star, okay, and then it should we are confining ourselves to control affine system which are square. In addition to that, there is no singularity in this particular matrix actually, that is all we are interested. And before we proceed further, remember this t goes to infinity and all does not really mean t really goes to infinity. This is a like notationally we always do that. What it means is asymptotic tracking actually. Okay. So, and then what time it will close in and all that, it will depend on the settling time that we choose. Ideally speaking, it will never close in, in the zero error sense basically, but it will approach to almost zero error in some sort of a settling time that we consider in this problem actually. Okay. All right, now proceed further. Let us go back and try to see what control values should take, or in other words what is the control solution for this problem, so that this objective is met actually. How do we do that? So, before doing that, let us see what is our output dynamics, as what we have is state dynamics actually. Okay. So, we need to consider what is our output dynamics first actually, okay, so that we can talk about output error dynamics, and that error dynamics needs to be some sort of a stable linear dynamics actually. Okay. So, first we need what is our output dynamics. So, now remember y equal to h of x, that is where we will start with, because y equal to h of x, okay, then if we take derivative both sides, y dot equal to this del h by del x into x dot, okay, because y equal to h of x actually, that is why. and x dot we know that is f of x plus g of x times u. So, we will substitute that is where we substitute, and then try to simplify this matrix multiplied by f of x is f y of x, and this matrix, this del h by del x, remember this in general is a matrix by the way. So, this del h by del x into g of x is what is defined as g y of x, and that is what g y of x is all about. Okay. So, g y of x is nothing but del h by del x into g of x, that is g y of x. Okay. So, that is our output dynamics. Now, we have to talk about an error dynamics actually. So, what is error? Error is y minus y star. Okay. That is what that is our error of output tracking. So, in that what is error dynamics then? So, let us talk about E dot, and then what we really want, the error dynamics needs to be some sort of a stable first order dynamics, let us say. Okay. By the way, with this del h by del x is defined that way. Okay. So, this del h obviously it is a Jacobian matrix. So, that is defined that way in partial derivative sense and all that actually. Okay. And now, this okay. Now, coming back, this you define this error like that, y minus y star sort of thing, and do some control design u in such a way that the E of t should always see some sort of a stable first order, I mean like time invariant linear dynamics actually. So, how do you do? We will need to enforce this dynamics by some gain selection k, which will come and operate here actually. Okay. So, and most likely we will see some sort of a fixed gain k, that is what most of the time we will be able to operate. That means just one gain, okay, we will be able to operate E dot plus k equal to 0, and then that scheduling and all we will see. If necessary, you can always do some limited amount of scheduling. In other words, you keep on changing this dynamics as you go along actually. But theoretically speaking, if you really want to operate this dynamics as some sort of a linear time invariant first order aerodynamics, then k has to be fixed actually, it should not be varying at all. Okay. Then only it will be some sort of a LTI system, linear time invariant system. Okay. Anyway, so coming back to this is like E dot plus k equal to 0. Okay. So, that means that is what we want to do. We design a control in such a way that this dynamics should always be like this, let us say. Okay. So, that means this if this dynamics is continuously satisfied, that means the solution is like that, E equal to e to the power minus k t times E 0. Okay. If this is the dynamics where k is the control gain, fixed gain let us say, and k is positive definite, in a scalar sense it is positive, but in metric sense it is positive definite. Okay. Then what is that? That E solution of E is nothing but e to the power minus k t times E 0, and certainly this one e to the power minus k t into E 0 goes to 0, because k is a positive definite matrix and hence minus k is a negative definite matrix. Okay. So, this E certainly goes to 0 as t goes to infinity. So, our controller should do such a good job that it should keep on satisfying this aerodynamics no matter what actually. Okay. Whatever is the operating condition at whatever point of time, it should continuously try to enforce this system dynamics actually. Okay. So, that is what the entire philosophy is all about actually. Okay. Now, the question here is, how do you select a gain matrix k? First of all, because it is a matrix after all, when it needs to be positive definite. So, how do we go ahead and select that? And one easy way to do that is to select a diagonal gain matrix k, and because the diagonal, if it is any matrix is diagonal, then the eigenvalues are the diagonal elements actually. So, if you simply select a gain matrix as diagonal matrix with positive elements in the diagonal entries, basically all the diagonal entries needs to be positive numbers, and then obviously this gain matrix will be positive definite. And how do you select those positive numbers? We will select in a reverse way, telling that okay, I will select the gain matrix k, okay, some sort k equal to some sort of a k1, k2 like that. Okay, I will select kp or km whatever I have. Okay. Then this ki that we are talking about will be ki is 1 over tau I, and this tau I is selected based on the philosophy that okay, the settling time is nothing but 4 tau I. So, in any design, if you have a settling time specification, then you can select a appropriate tau for that, because 4 tau is settling time. So, you can compute the tau, and you can compute the gain like 1 over tau, and then these gains will go as diagonal entries in this gain matrix k. Okay. So, my strong suggestion is always to operate from time domain specifications like this, instead of looking at your behavior later and all that. Once you, if you want to implement this control in any problem, start with some specifications like that, then reverse compute your gain, that should go into the diagonal elements actually. So, that this error dynamics will continuously satisfy this kind of I mean this kind of settling time property actually. Now, second thing to note is, if you have diagonal elements actually in the for the gain matrix, then if you go back to this dynamics, okay, this E dot plus K E whatever you are talking about here, okay, this E dot plus K E, this one if I have this gains as diagonal element, then individually I can think it E I dot plus K I E I equal to 0. That means, any E I is not a function of any E I minus 1 I plus 1 nothing actually, it becomes an independent dynamics by itself. So, that is how you get decoupling behavior in this dynamics directly basically. For example, linear dynamics, I mean this longitudinal and lateral dynamics you want to decouple, then this will automatically give decoupling in each of the channel actually. Okay. So, that is another nice behavior of this control design basically. Anyway, so coming back to this is what we want to kind of enforce or satisfy, okay, for our plant. So, how do you design a controller to satisfy this dynamics? That becomes some sort of a very straightforward approach, because we know the definition of E now, y equal to y minus y star. So, just substitute E equal to y minus y star, and then E dot is nothing but y dot minus y star dot, where y dot is already was something that we computed. This is what we computed y dot. So, y dot to substitute, y dot is f y of x plus g y of x times u, and then take everything else to the right hand side, and ultimately you try to solve for u. And remember this assumption that we have done, that p equal to m, that means g y of x is certainly a square matrix, and g y of x is non-singular for all time. That's the reason, that's why we assume that g y of x we have assumed that is non-singular, it is square and non-singular for all time, that is by assumption actually. So, we should be able to do an inverse, I mean we should be able to solve control for here. I mean from this equation, if you want to solve the control variable, this takes this form actually. Okay. So, ultimately the control formula is like this. Okay. And remember, this matrix has an inversion, and this is a dynamic matrix, that means it keeps on changing with time, and that is perhaps the reason why it is called dynamic inversion actually. The matrix, one matrix inversion needs to be taken all the time, and that matrix itself keeps on changing in a dynamic manner. So, that is why it is a dynamic inversion actually. Okay. So, we get a solution for the controller this way. Okay. Alright. So, if everything is clear by now, I hope so, then we will proceed further and see some of these discussions around that. The basic philosophy is like this: we have a output to output tracking problem, and we have the output dynamics. On the way, we assume that this problem is square, and this g y of x is non-singular. G y of x is clearly defined, that the del s by del x into g of x, del s by del x is like that, and g of x is already known to us. So, we will be able to do all these computations in a nice way. F y we know, g y we know, and if you plug in all this error dynamics in this formula, then we will be able to compute u as a function of all this known information actually. We know y star, we know y star dot, they are coming from the command reference side actually, then y is already available with us, f y is known to us, and g y is also known to us. So, we will be able to compute our controller in a direct manner. Now, we have started from here, then gone here, then gone here, and then gone here actually, but you remember that none of the steps are only one sided. That means, you can start from here and go there and go there and go there in a reverse. These are all implies and implied by relationships. Okay. As long as like the control can be computed in a continuous manner like this actually. Okay. Most of the time implementation sense we compute it in some sort of a zero order hold sense. Okay. Then we will not be able to do that reverse way in a very precise mathematical manner, but as long as delta t's are small, we can consider that as continuous variable, and all these relationships are implies and implied by. That means, if the control is computed like this, and there is absolutely no problem in implementing this control magnitude whatever it is. I mean there are practical problems, as we all know actually. For example, this control that you compute can go out of bound. If there is out of bound and you just cannot implement it, this formula is no more valid. So, obviously, at that point of time this dynamics is no more valid. Okay. So, if it violates, similarly if it violates like rate constraint or something, then also this dynamics is not valid. So, like that there are several issues that will pop up here, okay. And then we will try to kind of see what all issues are there actually. But as long as these issues are not there, none of the issues are relevant, and in other words this control you are able to implement in reality in a continuous manner, then this is the dynamics that you are enforcing, and hence E has to go to 0, and E goes to 0 in an exponential manner, remember that. It is not necessarily only in asymptotic manner, but it is an exponential manner actually. So, what are the I mean before we proceed further, let us see some sort of a toy problem, design problem sort of thing. So, it is a very simple one dimensional problem where you have x dot equal to this dynamics, okay. Remember this g of x 1 plus x square will never become singular, no matter whatever x value is that, and objective that is just regulation, that means y should go to 0 and y here is nothing but x. So, we know x star or y star is 0 and y star dot is also 0, okay. F of x is this one, g of x is that one, and because y equal to x, so del s by del x is 1, so that means f y is this one only, sorry, f y is this one, f y of x, and g y of x is also that, right, del s by del x is 1 anyway. So, we do not have this difference actually. So, what is the desired aerodynamics? Let us say E dot plus k equal to 0, where k is 1 by tau, which is certainly greater than 0. Then you substitute whatever you know actually. Y dot is nothing but x dot. So, x dot is all that actually whatever you see here, that is what is substituted here. Y star dot is 0, so y star is 0 for all time. So, y star dot is 0 actually, and y star is also 0. So, substitute 0. So, you will ultimately what you are doing is this entire expression plus k times x would be 0, okay. So, that means u is equal to this, you solve it in a kind of inverse way basically, and then from this equation if you solve for u, this is the control formula. So, that is so, and this control formula is guaranteed to satisfy this kind of aerodynamics, okay. That means this controller will certainly lead to stable behavior of the plant. In other words, x will be driven to 0 actually, no doubt about that actually, okay. This is simply a demonstrative toy problem, that is all actually. Now, the question is the first order aerodynamics always enforced? Will you always be able to do that? And answer turns out to be no, okay. And because suppose the u is not there here, but just let us say 2 dimensional 3 dimensional problem, and we all know that is in controllable canonical form and all that, x1 dot is x2, x2 dot is x3 like that actually. The control variable is not there in the output variable. Suppose it is y is x1 and x1 dot is x2, then y dot is x2 and there is no control variable. So, we will not be able to operate that based on a first order plant actually. So, what is the answer to that then? The first order, if the first order dynamics is not always enforced, okay, then there is a concept of something called relative degree actually. So, what is relative degree? This is defined as the number of times the output needs to be differentiated, so that the control variable appears explicitly, okay. And based on that dynamics, wherever the control variable appears explicitly, you enforce an aerodynamics of that order. And we all know that linear system, LTI systems theory, linear time invariant system theory, any order linear dynamics can be enforced. You select those number of poles or things like that, and you must suppose you have this fourth order polynomial you have to select, or fourth order aerodynamics that you need to select. Then how do you do that? This is rather easy. So, you have this okay, you have this, let us say mu1 up to mu4, let us say. So, these are the desired eigenvalue location, like whatever we did in pole placement control design. So, what you do here is like s minus mu1 into, or lambda minus mu1 either way, into s minus mu2 into s minus mu3 into s minus mu4 equal to 0 if you put that, okay. Then that means the pole locations are certainly mu1, mu2, mu3, mu4, which are stable actually whatever way you select, okay. These are locations whatever you select, and okay. Okay. So, if you expand this expression, it will give you some sort of s fourth plus something times s cube plus like that actually, right, something times s plus something equal to 0. So, this is the fourth order dynamics. That means, if I take this one and then tell okay, this is my E fourth plus this one whatever is here, that will be same as times E q and things like that, plus something times E, okay, equal to 0. That is the stable dynamics that I will select actually. So, whatever is the coefficient that goes on here, that will help me in enforcing a stable dynamics actually, okay. This is not difficult to select whatever order actually there. So, that is not a problem at all. Okay. All right. So, coming back to this. Okay. So, the second order, suppose you need to fix a second order aerodynamics, okay, and then you have to enforce some sort of a dynamics like that, where Kb is turns out to be the diagonal matrix of like that, and this Kp turns out to be a diagonal matrix of this one. So, again this individual element sense you are operating on kind of in a decoupled manner and things like that actually, if you select all these diagonal matrices. Now, there is a concept of this relative, okay, remember that the relative degree can differ from various channels actually, that means y1 can have relative degree 2, y2 can have relative degree 3 like that actually, and then the total relative degree turns out to be addition of all these individual relative degrees. What I have shown here is possible only if all the channels will have second relative degree 2 basically. If it is different relative degrees, you have to enforce different aerodynamics in different channels actually. Okay, so that is also possible actually that way. Okay, so if the second order aerodynamics needs to be enforced, then the corresponding equation is like that. You start from here and then simply substitute what is E dot, E double dot, all that actually, and ultimately you will end up with y double dot, and y double dot will contain u, and then you will be able to solve for u basically. So that's the whole idea there. So example again, let us see this. This is like a second order system. X1 dot is that, X2 dot is that, and the objective is both the states should go to 0. St goes to infinity, let us say, and in general we may not be able to do that for arbitrary signal tracking, because there is a theorem that we will see later actually, but for regulator problem it is possible to do. Okay. So, what we do here, it is very tempting to see first of all that okay, the x1 dot and x2 dot is there anyway. Okay. So, what you do here is, suppose because x1 should also go to 0, it is very tempting for me to select y as x1, because I will be able to do that, because if I select x1, y dot contains u. So, if I select y dot plus ky equal to 0 sort of thing, then I will be able to enforce that x1 should go to 0, and that is one of the objective anyway. Okay, but the problem is once x1 goes to 0, x2 dot goes to 0, that means there is no change of x2 after that. Okay. So, that means even though I will be able to stabilize x1 to, I mean I will be able to drive x1 to 0 from any initial condition, I may not be able to do the same for x2 actually. Okay. On the way x2 dot can go to 0, and once x2 dot goes to 0, there is no change of x2 basically. Okay. So, that's the reason selecting y1, I mean selecting y as x1 is not a good idea actually. So, let us select y as x2 then, okay, and that is why I have written that selecting proper y is crucial. Okay, so, let us select x1 y as x2, then what happens, let us say y dot is x2 dot, it does not contain u, okay, but y double dot is 3x1 dot, it contains u. Okay. So, then what we do, we select a desired output and all that, that is y star is 0. So, y star dot double dot are all 0. Okay. So, the aerodynamics now, because y double dot contains control, we have to select a double dot, I mean this second order dynamics sort of thing, and then enforce this dynamics. By enforcing this dynamics, what we mean is the enforcement of this dynamics actually. Okay. Now, what is the beauty of this dynamics? Not only E goes to 0, okay, but E dot also goes to 0. Okay. Second order dynamics, all that E goes to 0, E dot also goes to 0 simultaneously actually, as t goes to infinity of course. Okay. So, if E dot goes to 0, that means x2 dot goes to 0, and x2 dot goes to 0 means x1 goes to 0. Okay. And E goes to 0 means x2 goes to 0 anyway basically. So, x2 goes to 0 as E goes to 0, and E dot goes to 0 means x2 dot goes to 0, that means x1 goes to 0 also. So, both the things will go to 0 actually that way. So, that is how we have selected a, I mean kind of a intelligent manner y should be x2 basically. Alright. So, we continue further like that, we select this aerodynamics and all that, then it leads to that kind of a dynamics, and hence there is a control solution for that, because x2 double dot contains, this is x2 double dot, right, y is x2 now. So, y dot is x2 double dot, there is a u term here. So, we will be able to solve it for that actually. Okay. And also remember that this term what you see in denominator has no singularity, I mean it does not go to 0 actually, this expression has no singularity actually. Okay. And that is possibly because we have selected this example artificially, it is another kind of toy problem actually. In general it may not have that nice feature actually. Okay. So, when does the dynamic inversion fail? That is another condition that we have to worry about. So, what is the fundamental principle of dynamic inversion? It turns out that you differentiate y repeatedly until the input u appears, and then design u to cancel the nonlinearity and enforce some sort of a stable aerodynamics, right. That is what we do, that is the fundamental principle. So, is it possible to design u this way always? And that turns out the answer is not necessarily, and the concept here is it is possible only if the relative degree is well defined actually. Now, the question is what is well defined relative degree obviously. So, these are all like further questions after questions which will show us to more and more towards differential geometry concept actually. But anyway, what is well defined relative degree? Let me kind of simplify this idea from a counter example point of view. The question is what is undefined relative degree? Whatever is not defined is well defined in that sense. Okay, so, undefined relative degree is something like this. It may so happen that upon successive differentiation of y, u appears, okay, but the coefficient of u may vanish at some point x 0 in the domain actually. The coefficient has an expression, but that expression goes to 0 at some point x 0 in the domain. Then what you have actually? You almost do not have it, that expression. You have it everywhere, but some point of time you do not have actually. Okay. So, in those situations the relative degree is not defined, okay, at x 0. It is defined everywhere, but it is not defined around at x 0, because arbitrarily close to x 0 it is non singular, but on x 0 it is singular. So, in that sense these are like confusing, and these are in that sense we tell relative degree is undefined actually. So, in example sense that is what it is, x 1 dot is x 2, let us say x 2 dot is some expression of x 1 and x 2, but u appears plus u basically, and if you select y equal to x 1 square where rho is some nonlinear function and all, then you carry out and say that okay, y dot is this expression, y dot is 2 x 1 and 2 x 1 dot, and x 1 dot is x 2. So, I will substitute the get it 2 x 1 x 2, and y double dot is 2 times x 1 times x 2 dot plus 2 x 1 dot times x 2. So, I will have this expression actually. Okay. So, obviously, this y double dot my control appears. So, I have to enforce a double kind of double derivative and things like that. So, y double dot is like this, that is ultimately it will guarantee whether the relative degree is defined or not. So, what is relative degree? This g y of x is like this, right, 2 x 1 basically. So, as x 1 goes to 0, then certainly g y of x 0, and here is a problem actually. So, if I draw this phase plot or something, we have x 1 and x 2, right, this x 1 and x 2. Okay. So, x 1 0 means what? And the entire imaginary line x 1 is 0, right. So, entire imaginary line not imaginary, the x 2 axis basically, entire x 2 axis, x 1 is 0. So, on that entire x 2 axis of this phase plane I have a problem of not defined relative degree basically, relative degree is not well defined actually. Okay. So, what if you choose y equal to x 1 then, and this problem happened because we selected x 1 square. Okay. If you select x 1, then this problem does not appear, because y dot is 2 x 1 and all that, the 2 x 1 term comes from this expression, right, because y is x 1 square, come on here, y is x 1 square. So, y dot is 2 x 1 times x 1. So, this 2 x 1 fellow comes from because of that fact actually. Okay. So, what if you select x 1 instead of x 1 square, then obviously this y dot is x 1 dot which is x 2 and y double dot is x 2 dot, okay, which is like that. So, the coefficient of u is 1 now, it is not an expression really, it is just 1, and obviously 1 is not equal to 0, and that is true globally, and hence this relative degree is well defined globally actually. Okay. So, these relative degrees are well defined, then obviously you can discuss about this like dynamic inversion is possible actually. Okay. All right. Now, what are the advantages to summarize of DI design? First of all, it is a very simple design. As far as the understanding of mathematics and other things are concerned, I do not think that is it requires too much of understanding of complicated math and things like that to understand why it works and all that. So, it is some sort of a very simpler design in my view actually, and obviously there is no need of tedious gain scheduling, okay, because what we really started with, gain scheduling demands lot of operating points, and then you design local controllers from linear system and then interpolate all sort of things are not required. So, as long as the control is not an issue, you can keep on enforcing this aerodynamics, right, and then you keep on getting a stable behavior no matter whatever is your y star basically. So, wherever you are operating basically. Okay. So, I mean in some sense the scheduling the gain has a different advantage because of other issues. For example, you want to avoid the slew rate limit or the control derivative limit and all that actually. So, probably you tune the gain a little bit as an automatic function somewhere. So, then it may help you actually. I mean that is sometimes people do that, and that is there also they do not make use of like a high varying gain and all that actually. It is a slow varying parameter something you will introduce to have additional advantage, but in principle you do not need to do that. You just select a fixed gain k and then you are done actually. So, gain scheduling is not required. Okay. And hence sometimes this dynamic inversion design is also known as universal gain scheduling design. Okay. Because the gain scheduling is not required, it operates everywhere and things like that. So, it is also known as universal gain scheduling design, and also known as what I did not write it here, is also known as some sort of a nonlinear PID design. But ultimately if you go back to that expression, what it really operates, E dot equal to minus k E sort of thing. Okay. So, if you see that this is actually operating on P gain actually. Okay. E dot is minus k E. So, the k times E is nothing but proportional term actually. So, it is operating on some sort of a P gain. Now, there is nothing wrong in operating based on a Pi gain. Say somebody can always tell k1 times E plus k2 times integral of E equal to 0, that is also possible. So, that will become Pi design. Okay. If you have a second order dynamics and things like that, this is already a PD design. There is a P term and there is a E dot term. Okay. So, there is already a PD design. You can always make it plus some gain times integral of E. So, it will become PID design basically. So, that way it is also called as nonlinear PID design. So, all the advantages of PID design tuning and also the things can be brought in here, and that gives additional degree of comfort and power for the control designer actually. Number 2, it is easy for online implementation because it leads ultimately leads to closed form solution. So, control is actually after all a formula. So, as long as you have the state information, you can compute the formula directly, just one expression actually. So, there is no sort of not necessary to have some sort of like this 2-point boundary value for problems in optimal control, and then robust control design you talk 2 Riccati equations, things like that. Don't do all sort of things. It is just a formula that you want to evaluate and carry on actually. So, it is very easy for online implementation. Now, asymptotic rather exponential stability is guaranteed for the error dynamics, and of course, as I keep on telling, is subjected to control availability basically. If your control is not saturated, it is still within the bound, rates are not an issue, then it is that expression that you have derived, it can be interpreted in a reverse way. You start from here, then go there actually, because this expression is not compromised. Okay. So, whatever you are computing, you are able to give that. So, ultimately you are enforcing this one actually, this dynamics, and that is why this asymptotic rather exponential stability is guaranteed for the error dynamics, because if you see that the solution, we all started with this solution actually, and this solution is actually exponentially decaying. It is all based on LTI theory. LTI linear time invariant theory is always globally exponentially stable because of this beautiful theory. As far as output tracking is concerned, remember this is all about output error. As far as output tracking is concerned, it satisfies global exponential stability actually. Okay. So, of course, subject to control availability. And the big problem that we discussed in gain scheduling, that what if the parameters are updated, that means you have a design redesign or design update and things like that. Certainly not a major issue, because all the parameter values can directly go into the formula actually. Whatever you have a formula for control, you can directly take it and then make it operate. You do not start with a kind of sequence of nonlinear, I mean sequence of linearized plant and then linearized, I mean then design gains and things like that. We do not have to do that. You have a control formula, you simply plug it and operate actually. So, these are all the major advantages: simpler design, easy online implementation, asymptotic stability is guaranteed for the error dynamics, for the tracking error sort of thing, and not a major issue if the system plant is updated or the parameters are updated. So, I think with all these in mind, we will stop here in this class and then continue with the further discussion of dynamic inversion in the next class actually. There are several issues and there are several remedies also. We will discuss the conceptual discussions we will do in the next class actually. All right, thanks a lot.